hit the questions in the time we have remaining. And I want to make sure, basically I'm going to hit what I think are the most exciting questions first, or the most useful. So let's go ahead and skip to, stop doing that, page width. Let's see. Okay, let's skip to question 2 of this exam, from, let's see, what school is this? From University of Washington. Okay, question 2. In this course, we've seen many different data structures. Here they all are. Directed acyclic graph, right? They list that as a specific data structure. For most of the following applications, for each of the following applications, indicate which of these data structures would be the most suitable. A list, a linked list or linked list or an array list, a 2D or higher array, a stack, a queue, a hash table, in other words, a map or set, tree, binary search tree, undirected graph, directed graph, or directed acyclic graph, right? Which of these data structures is the most suitable? And if it's a data structure like a tree and a graph, describe what information is stored in the vertices and edges, and if the edges are weighted, describe what's in the weights. Okay. So, A, a map of the Puget Sound highway system used to display traffic travel times on the web page. The map displays the principal cities, the intersections, and the major landmarks, the roads that connect them, and the travel times along these roads. Travel times along the same road may be different in different directions. So what data structure should we use to model this? A directed graph. That's exactly right. So in this case, what are the nodes? Cities, landmarks, the places you want to get to, right? And the places you want to get to are so this is actually a classic thing for graphs, mapping something, basically representing a physical map. Things you want to get to are the nodes. How do you get to them? The edges. And so, do they have weights? Yeah, the travel time. The travel time should be the weights. Okay.
Intersections. What about that?
That would probably be it. Those are vertices as well, okay, right? Because you have a travel time to a certain intersection, which kind of makes you start thinking of how in the world do you create something like Google Maps and like figure out what the travel time is between different directions and stuff. And the answer is you pay a lot of engineers a lot of money and let them figure it out. It's a big problem with the big question. Chessboards. An 8x8 board used for a game of chess. Each square on the board is either empty or it contains a chess piece. So what data structure would we want to use here?
2D array.
A 2D array. Yeah, 2D array, right? We could do a 2D array of integers or characters, right? A computer model showing the dependencies between the steps needed to assemble a B-787 airplane at Boeing's Everett plant. Yes?
There is no extension of 2D array lists.
Right, and yeah, it's just 2D array there, right? It's mentioned there. So for this one, a dependency, a computer model that shows the dependencies. What data structure? Not linked list. A directed acyclic graph. Directed acyclic graphs are used for dependencies, right? Because they're like with course requirement, because like with directed acyclic graphs, that was how we would use course requirements. Anytime you have something where you're trying to figure out what goes before what are dependencies, we want to use a directed acyclic graph to model that.
Oh, because they can be parallel processes.
Right. Like for instance, and I mean that kind of has its prerequisites. So let's say I want to install a program like sudo apt install. Let's see, what's the program that's Eclipse? Sure. Plug in my password, right? To install Eclipse, I have to install all these additional packages that Eclipse depends on, and those packages might depend on other things. So it uses a dependency. So this would use the same kind of stuff that a dependency graph. I mean, I don't know if it uses a dependency graph, but that's how I would solve it, a dependency graph, to figure out what software needs what, until I get to something that doesn't need any requirements, right? Let's not install Eclipse today. Okay. a list of legal words in a Scrabble game. We want to quickly be able to check whether words used by players do in fact exist in the list. Hash map. Hash map would work because we could check if or hash set specifically.
Hash set, yeah.
Yeah, because we could create a set of all the legal words in Scrabble, and then if it and then just simply ask in constant time, does the set contains this word, right? You could, if you wanted to be space efficient about it, use a sorted array, right? And then do binary search. Let's see. Description of the inheritance relationships between classes and interfaces in a Java program. So that would be a tree because that's a hierarchical thing. If you remember the slides, right, you had like list and then all the implementations of list and then you had all this, so the sub-implementations of those kind of lists, right? The history list recording sites visited by the user of a web browser. As new sites are visited, they are added to the list. The list also supports the operation of going back to the web page that was previously visited and going forward to the next page visited. You could use a doubly linked list. You could also use two stacks, right? Where basically the top, where basically if you need to go forward, you just simply pop your current thing into the forward stack, right? Right. You could use two stacks. You could use a linked list. There's a number of good answers for this one. Okay. Okay. The nodes in an integer binary tree can be represented by the following data structure, right? Binary tree node, int item, left, right. Complete the definition of the method BFS to perform a breadth first traversal of a binary tree and print out the node values in the order they're reached during the search. This is saying what the other exam was saying to do, a level order traversal. Write the code to perform a level order traversal. In your solution, you can create and use instances of what other standard data structures, lists, queues, stacks, trees, hash tables, graphs, or whatever. We didn't cover whatevers, but they're a very useful data structure. I know, I'm terrible. Their operations, if they're useful, and again, in our final exam, you can, if you see a problem and you're like, man, I really wish I could create a data structure, then create the data structure. Okay. So let's go ahead and I'll boot up Guinea so that we can have at least a more. So let's zoom in a bit and view. Is this, yeah, okay. Good. So let's go ahead and grab, I don't need you anymore. I said close without saving. So let's go ahead and grab, don't need this. Grab this. So this is written as an instance method. That doesn't really matter. Right, but we're doing a breadth first traversal of a binary search tree, right? Which means we don't want to do it recursively. We want to use a queue to do that, right? So let's go ahead and just simply do that. We don't even need to use and this is even an easier binary search tree because we don't even, I don't think we even have to use a queue because there's only one way to get to each node, right? There's no cycles, and that's why we have to use we have to use, well, actually, we do want to use a queue. We don't have to use a set. That's what I meant to say. We don't have to keep track of what nodes we've already seen because there's only one way to get it to each node because there's no cycles. So queue of BT node queue is equal to a new. I don't think you can create a queue, right? It's an interface, right? So that's would be in. I mean, if you do that on an exam, that's perfectly fine. Linked list of BT node, right? Right, so we create a new queue. We're going to start at root R, R dot, and what is it? It's pull, what is it? It's pull to get out, and what is it to put in a queue? Offer. Yeah, it's something weird like that. If you put something else like NQ and DQ, I'm just going to count it right because, that's a much better terminology for queue. So offer the root to the queue. While not queue dot empty. I think it's like I prefer to use the term is empty, but that's the way it's done properly in Java, I think. While queue is not empty, while there's still something in the queue, BT node current is equal to queue dot pull, right? Get the first thing off, get the thing that's in the front of the queue off of the queue, and now we'll print it out because it says we want to print it out. System.out.println queue dot. Why do you keep disconnecting? Okay. Print out current dot item. Print current dot item. And now we got to add our children, right? So we visit ourselves. Now we add our children to be traversed to. So if current dot left is not equal to null, add it to the queue. Queue dot offer current dot left, right, and then the same thing for my right node, right? Which, I mean, I haven't had a student do do the exact same, but except for the right side, you know, on an exam. I haven't seen a student be quite that daring yet, but I'd probably accept it. But, you know, while it's not empty, pull it, print out your current item. If you have a left child, add it to the queue. If you have a right child, add it to the queue. Then we're going to go, so this will visit the root, then it's going to visit the root's left child, and then the right child, and then the root's left children, left and right children, and then the root's right child, left and right child, right? That's the order. So this will go across in level order traversal. So it's fairly straightforward, not recursive, right? Whenever you want to do something breadth first shaped, use a queue. It makes it really easy. All right, let's see. Adjacency list. We'll go a bit back to that. While we're still coding, I want to go to I want to actually skip to one of the other exams because they have one of my favorite coding questions that I've seen on an exam because it's a great question, and it's one of those questions that makes you break out into a cold sweat when you see it on an exam. It's really not so bad okay? So this one is at USC. You are given a text file containing a week's worth of login duration for users on aludra.usc.edu. Okay, and before I continue, they're assuming that we're working in C++, but we'll just simply do it in Java. Okay, it should be fairly straightforward to kind of grok what we're getting. So we've got a week's worth of login information. We've got this file. Okay, each line of this file corresponds to a single login session. A line contains a user ID, for instance, Cheng W, followed by a space, followed by the user's login duration in seconds. For instance, Cheng W was logged in for 3.14-326 for that login section. Your job is to compute and print out the average login duration for each user. So, i.e., add up all the durations for that user, divide it by the number of login sessions for that user. For example, if the input file contains 2 login sessions for Cheng W, one for 314.326 sessions and one for 204.7 seconds, then Cheng W 259.513 should appear exactly once in your file. The input file is unordered, and you may assume the input file is unordered, and you may assume the input file is well formed, so you don't have to validate the input. In other words, your input file won't have anything that will make your computer crash so long as you're parsing it correctly. Your output does not need to be sorted. Please write a partial C++ program to perform this task. You can assume that the correct header files have been included in order to, so in other words, you don't have to import anything. In order to receive any credit for this problem, you must use at least 2 standard library maps. which is a nice hint for how to solve this. One to store the duration of the sums for each user. Sorry, the sum of all the durations, and one to store the login sessions for each user. So it's telling us this is a map program. This is a counting program. This is a counting problem, right? Because for what we need to do to solve this is that for each user, we need to figure out how many times they logged in and the total amount of time they were logged in, and get the average amount of time they were logged in for, which is the total amount of time they were logged in divided by the number of times they logged in, right? Now, we could go through the file and try to sum that up, but that would be a pain, right? Going through a file multiple times is actually rather annoying. So we're just going to go through that file once and build it up from there. So this is a file writing question. So let's go ahead and write this. Public static void. Let's see. Should I boot it up IntelliJ? Now I'll do it here. Public static void. I should torture myself since you guys don't get to use autocomplete stuff too much. Public static void map. What am I going to return? I'll figure that out later. I'll figure it out now. User, which should be a string, and the amount of time they were logged in for. So that should be a double. So public static map string double. And so what are we going to take in? Some. This should be called average login or something like that. And we're going to take in a file, I guess, or a file name. Sure. String file name. And this is over here is something that I would not expect you to be able to do. Sorry, I'm not going to expect of you. Right? Normally we would throw it into a try-catch block because this would be because we're reading something and that needs to be in a try-catch block. I'm going to obviate the need for a try-catch block by just simply saying that this will possibly cause an exception. And saying if you call this method, it needs to be in a try-catch block. Okay, that's what throws exception says. It says this needs to be in a try-catch block because something could go terribly wrong. This will just prevent me from having to do extra indentation. Okay, so but if you forgot to do that, or even the try-catch block and you're on an exam, I'd go meh because I'm probably not going to teach file I/O on this exam. It's not something I'm testing. I'm testing can you use data structures. So let's start by creating our scanner. Scanner. So scanner is equal to new scanner new file made from file name, right? So we've created our file. This is what would need to go in the try-catch block, right? Where we found, because there would be a file not found exception, right? So we want to read this file. We're going to use scanner to do so. So now we need to read it. So while scanner dot has next line, I'm going to read this one line at a time, right? Scanner dot next line, right? This will read a line, and I'm kind of doing this in reverse because I sometimes accidentally do that. String line is equal to read the line, right? So this will read all the lines of text. So at least I've gotten some points there, right? I can at least read a file. So now I need to parse this file. It's separated into, so the file is separated into two parts, right? It's a string, space, and then a string, which is actually a double, right? So let's split it up into those two parts. String parts.
Why not you use next?
Because I don't like doing that. I want to be able to, because I like atomically working with single lines at a time, right? I have file, which is split up into lines, and then I can figure out how to split up the lines, right? That's how I like doing it. Has next would basically be reading part, then read part, and I don't want to have to keep track of how many parts I've read,
Okay.
right? That's just me. But anyway, the parts are, right, so string array parts, there's two parts for it, is equal to line dot split. Right, I think it's split in Java. When I'm working with this next semester is going to be terrible because I'm going to be working in Python and I'm going to be like messing up all the function calls and stuff. So we're going to split on the space, and it will give us a this will basically give us an size 2 array, where 0 is the username. So let's go ahead and get that. String username is equal to parts 0, and then string, and then let's see, double login time is equal to parts 1, which you shouldn't do on it, which would be a minor penalty on an exam, but obviously you can't do that, so we need to convert it using double.parse double, right? Int.parseInt is not too easy to figure. It's not hard to realize that there's a, there was integer.parseInt, there's a double.parseDouble, which turns it into a double. We don't have to worry about the space because line.split got rid of it, right? So we've got our username, and then we've got our login time. Okay? In fact, I'll go ahead and limit and turn this down to user and login time. That'll be fine. Okay. So now we need so we've got our scanner. Now we need our maps, right? So let's do our first map over here. Map string double login times is equal to new hash map, right? And we can assume everything's imported, right? So this will say for each, the key is the user, or the username rather, and the value is the amount of time they've been logged in for. Over here, I'm going to use another map to keep track. String is the user, and the integer, I'm using an integer here because this will be, he called it count. I'm going to just call it num logins, right? How many times did this person log in? Hash map. And you might be realizing that this is an actual program that somebody probably had to write at some point, right? To figure out, okay, who's using, how long are the average login sessions? How long do our students log in for, right? Or, what is kind of the distribution of their average login sessions, right? What kind of, right? So we've got our login times and the number of logins. So now I'm going to leverage a fact over here that if we've seen them before in one of these maps, then we've seen them in both maps, right? If the key exists in one map, it's going to exist in both maps. You can't exist in one and not the other, right? So let's go ahead and start with num logins. So if num logins dot contains, so first off, if it does not contain contains key user. So if we haven't seen the user before in the number of times they've logged in, then we also haven't seen them in the login times yet. So we'll initialize both of them right here. Login time. So login times is dot put. Yeah. So we have, right. Actually, I'll do num logins because I wasn't doing that first. Num logins dot put user 1. Login times user put user login time. Right? And that's something that you may be hugely irritated that I by, which I do, which is that I use a lot of pluralization and singulars, right? So I match them up. You put your login time in your login times. You put your line in your lines, right? That kind of stuff. Yes?
So you're assuming that if it doesn't exist in
one
non-logins, it's not going to exist in login time?
Yes. And that's a perfectly reasonable assumption to make, right? You can't have any time if you haven't logged in yet, right? And you can't have a time without having logged in, right? So it's a perfectly reasonable assumption in this case, right? Not always, but it's a perfectly reasonable assumption here, right? So if I haven't seen you. So if I haven't seen you, great, initialize you. Otherwise, I have seen you. in which case we need to update you, and I'm going to go ahead and do that in one line because I'm fancy like that. Put num logins, put user, and then num logins dot get user plus 1, right? And what this does, remember, is that it says, what are we putting in for the user? We're replacing it with the value that was previously there, and then we're adding 1 to that, right? We're essentially getting the number of times the user has already logged in, adding 1 to it, and overwriting the value for that user, right? Mainly because I wanted to do it in one line rather than two. And then for login times, we'll do the same. Put user login time dot get user, and rather than adding 1, we add login time, right? Which is, again, I'm sorry if that's irritating, login time versus login times, but it's something that I find very useful. Okay, so now that populates the 2 maps we need for that. Okay, so now we need to find the average for each user. Okay, so let's go ahead and do that. Okay, so for let's see, string user in num logins dot key set, right? This gets the set of all keys. And again, I'm taking advantage that basically every key in here is going to be in the other set, right? We want to basically find out the average. So let's assume we want to return that. So map string double averages is equal to new hash map for every user in the login set. So let's see, for every user who's logged in, who has a login, I'll go ahead and not do this in one line, but we want to get the number of times they logged in. I mean, we could, but int num login is equal to, int logins is equal to num logins dot get user, and then double time is equal to login time dot get user, right? So we get the number of time that user was logged in for and how many logins he had, and then for average, to figure out the average time or to compute it, we just do averages dot put user time divided by logins. And then we can return averages. We could also just print it out, or print out the map afterwards, but this gives it to us. And again, he didn't care about it being sorted or anything. That would just be converting it to some other data structure and then sorting that. Just be a bit more overhead. Now, I like this question because it's a great practice question because it's hideously complex for an actual exam. There's a lot of moving parts, which means it takes a lot of time to write, which means it's absolutely, here, let me zoom out so that you guys can kind of see it, and remove some white space. It's hideously complex for, right? How many lines was that? A lot, right? I mean, again, it's going to be on again, this video, I'm going to upload this video, so if you can't catch it here, don't worry too much about it. All right, my camera might not be great, but I can capture the screen fantastically. So, this is a lot of code for an exam. I like my exam questions to be able to be answered in 10 lines or less, mainly because if I think it's going to be in 10 lines or less, students will impress me with the amount of lines they can write. So, but this is a great practice problem because it's very, very complex, and has a lot of moving parts. But this is also, I also like it because it's a real world kind of deal, right? This is a kind of script that would be written for something, for it. So let's go ahead and take a look. So let's go ahead and switch back to the other exam. I just want to make sure, I didn't know how long that would take, so I want to make sure I had plenty of time to cover that one. So we'll switch back to the University of Washington exam now. So let's take a look at this next question over here. Here's an adjacency list representation of a directed graph. No unweighted directed graph. There's no weights assigned to each of these edges. Draw a picture of the graph. Okay, draw a picture of the graph that has the above adjacency list. Not something we really had to do before, so let's go ahead and do that. So we know there's 4 nodes, A, B, C, and D. How do I know there's 4 nodes? Because the list, it's a list of 4 nodes, right? A, B, C, and D. So now an adjacency list, right? It's typically a linked list, right? So A has edges to B, C, and D, and it's a directed graph. It mentioned that B, C, and D. B has an edge to A. C has an edge to B and D. So C can go to B, and C goes to D, and D doesn't go anywhere, right? So the other part of this question, another way to represent a graph is an adjacency matrix. Draw the adjacency matrix for this graph. Okay? And that's also easy. I'm going to just start, I'm not going to even bother with the graph because I'm going to assume that the graph you're going to draw is also a mess. So I'm going to just I'm just going to do it here. It always gets messy because, all right, so we have 4 nodes, A, B, C, D, A, B, C, D. And this is, just in case, remember, source over here, destination is our columns. Right, so A doesn't go to A, but it does go to B, C, and D. Awesome. B goes to A, but nowhere else. C goes to B and D. And D goes to nowhere. Oh, that was real easy right there. That's a real easy question, right? But it's a really valuable question, too. Okay, so let's see. So there's another Dijkstra's example over there.
So that was A goes to B and B goes to A, right?
A goes to B, B goes to A.
So the left side is A to B and then, okay.
Yep, A goes to B, B goes to A. Yep. Let's go ahead. Let's take a look at this one. We want to use Dijkstra's algorithm to determine the shortest path from vertex 1 to each of the other vertices. Update the entries in the following table to indicate the current shortest distance known and the predecessor. Cross out your own entries before you add new ones. So the initial distances are given for you. Below in the table, list of, so perform Dijkstra's algorithm on this graph, right? So let's just, this is a more interesting graph to do Dijkstra's algorithm on than our last time, so I'm gonna go ahead and do it again, because Dijkstra's algorithm is important, and honestly, the last one we did wasn't a great one. They all can't be winners, right? So let's go ahead and write down what we have. We have we have our done set, our to do, and on done and to do, when you've got a graph like this, you can of course just like draw on your graph and mark them off physically, right? Right, but here, because of the limitations of editing a PDF, I'm just going to put them over here. Then we've got our, our node, our distance, and our predecessor. Okay, and nodes are 1, well, they listed 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Obviously, the distance to 1 is 0, and it has no predecessor, whereas everybody else, right, so let's go ahead and initialize this. We're starting at 1. To do is everybody else. What? It told me start from vertex 1. We'll always tell you what to start with. And you'll almost always start from A, from S, or from 1, right? The ones we did were starting from C was a bit of a weird one. Or actually it was D. So anyway, so let's go ahead and initialize this. So distance to 2 is, our initial distance to 2 is 2, with predecessor is 1. Initial distance to 3 is infinity, with an, and we get there from 1. To get to 4, we go through 3 with it, and we get there from 1. To get to 5 and 6, that's an infinite cost. We go from 1, and we get there from 1. Okay, so let's go ahead and now iterate through this. So which of these that's not done is the cheapest one? That would be 2, so we move that into the done set. Now let's look at all the other edges that we can get from 2. This process is known as relaxing, by the way, figuring out what updating our distances, right? So we can get to 2 with a cost of 2. Now 2 has an edge to 3, so 2 plus 3 is equal to 5 to get to node 5. This is why I hate using numbers for nodes, by the way. So we can get to 5 with a cost of 5. Is that less than what we currently have as the cost, which is infinity? Yes, it is. So if we can get to there 5, cost of 2. Then we have an edge from 2 to 3. Its cost is 2, right? 2 plus 5, which is equal to 7. That's less than infinity. We put down 7 to get to 3 through 2. And that's all the edges out of 2. So now let's look at this graph again. We've got 3, 4, and 5, 7, 3, 5, and infinity. The cheapest cost is to get to 4. So we'll go ahead and select 4 as the next node to do. Move it from here to here. Okay. So now, and what they were telling to do is like scratch out the distance, scratch out your distances as you update them, but whatever. You can do that on paper. I don't want to make too much of a mess here. So 4 has one additional edge, which has a cost of 1, which goes to 3. So that's 3 plus 1. The cost to get to 4 is 3. 1 to get to 3. It's a total of 4. Is 4 currently what we cheaper than the current cost for 3? Yep, 4. So we'll put down 4. We want to get there, and we get there from 4. Okay, so now that's all the information that we can have updated. So now we have our costs are 4, 5, and infinity. Which one's the cheapest one? 4, 5, or infinity? 4 is, so we're going to use node 3. Next, so let's look at node 3. It only has one edge to update, which is as a cost of 2. So the cost to get to 3 is 4. We know, right? Because we look at our table at this point, right? We don't want to, it's not 7, it's 2, because that's what we have down. So 4 plus 2 is equal to 6 for cost to get to 6, and we're going to get there via 3, right? Okay, so we're done with that one. So now we have 5 and 6. 5 has a cost of 5, 6 has a cost of 6. So we'll say we're done with 5 now. Mark it done. 5 to get to here. So it costs 5 to get to 5, then 4 additional more to get to 6, for a grand total cost of 9 to get to 6, and that's not a better cost than 6. So no, we don't update any information, so we move on to 6. 6 has no additional edges, so we are done. So to get to 6, we'd go through 3. To get to 3, we'd go through 4. To get to 4, we'd start at 1. And to get to 1, well, we start there automatically. That's how that predecessor table works. All right.
Could you do an example
Of linked lists. We haven't done those in a while, so let's go ahead and see if there's a good linked list problem on one of these things. Shall we? That's a perfectly reasonable explanation. Let's go ahead. So, give me a second. Let me see if there's any. Let's see. Linked list questions. Just trying to think of one that's not terrible to go through. Because a lot of the interview ones are actually kind of terrible to do. Let's see, linked list. But yeah, that's fine. That's a perfectly fine question, because I found something earlier. Oh hey, here's something. No, I don't want that. Let's see. What would a good linked list question be? All right. I'm just trying to think of yes.
Well, I haven't coded this one out before, but questions like reverse a linked list recursively.
Recursively.
Yeah.
Or find the nth element from the end of a linked list.
The nth element from.
Add two numbers that are represented in Java by a linked list.
Oh,
with
yeah.
integers.
I've seen that. Oh, those are longer questions. Let's see. Recursively find the last nth element of a linked list. Right, that one. I know that. I recognize that one from cracking the coding interview, by the
Or
way.
nth.
The nth letter. The nth from the end. That's.
Yeah. Is that a long one too?
No, it's just.
Check if a linked list is a palindrome.
Check if a linked list is a palindrome. That. I mean, I'll do that. So, linked list is a palindrome. That's a fairly straightforward one. So the issue with the one where basically you're going for the nth one, those typically require you to. Those require They require doing something fancy, which is basically, I think that one requires you to like. So you have your seeker, which moves forward and counts how many items are in the linked list. And, well, actually, you would know how big it is. So to find the nth, the minus, you could just count. But if you don't know how big it is, then you have to find out how big it is, which would require. So the way you would do that is that you move basically. You have 2 pointers. One that moves 1 step at a time and iterates normally, and the other one moves basically 2 steps at a time, so it can count out. So it can count how many items are in it, and so then that gives you the. It's convoluted, but a check if a linked list is a palindrome. That's fairly straightforward, and doesn't require having me make a. I was just trying to figure out something I could do with static methods. So public static. Let's go ahead. Public static Boolean is palindrome linked list of string, or rather, strings are characters. Let's go with characters so I can compare. I can use the double equals to compare them, right? List, right? Is it represented by the same characters forward and back? Honestly, though, if it's a palindrome, then we could actually be asking if it's is it palindrome or palin? Yeah, that's the most important question here, obviously. Public static. Yeah, let's go ahead and make it generic of anything. EList. All right. So, fairly my answer, but would kind of this uses a bit of extra space. Would be queue was to create a queue, and to create a stack is to create a actually let's not make a queue. Let's make a stack. Stack is equal to new stack, right? And what we would do is just simply and so the key is though that when we're using a linked list is that we want to use the for each loop because otherwise when we iterate through it it's gonna take over n squared time because the get method we don't want to use the get method. That would slow us down. We want to use an iterator. So for e item in list stack dot push item. Yeah. So for every item on it, push that item onto the stack. For e item in list. So now for every item in the list, if e item, if item is not equals, so if item does not equal stack dot pop the item, yet return false because we just proved it wasn't a palindrome, right? Because there wasn't a match, right? Because because putting it in a stack will reverse the contents, right?
What is that? For E and list, that's in the same order?
Yeah, but the stack is reversed. So if we put it into the stack, it all goes in the reversed order. So we iterate through the list twice we go from item 0 to n, and then 0 to n minus 1, and then 0 to n minus 1 again. But we need to we created a reversed copy essentially by putting it into the stack. And then if we can get through the entire stack, return true. Now, of course, the next step in the question is somebody saying, well, that's fantastic. Can you do it without, using a stack, right? And again, you have to do something kind of clever with with the way you iterate through. And I don't think you could do it using it as if in a static method, right? You would have to actually have an instance method and be using, the .next to do that. Let's see, another common one.
There's another thing we do where they say fast pointer and a slow pointer, and one moves 2, one moves 1.
Yeah.
And that way one winds up in the middle, one winds up at the end.
Yes.
And then I guess I don't know to use that as a problem.
So that's why I was talking about how one moves, how you have 2 pointers. You can use a fast pointer. So that whole idea is that basically if you have one that is that starts, if you have 2 pointers, one starts and they both start at the head, you advance. So what you do is you here 1, 2, 3, 4, 5, 6, right? You're starting so you have your first pointer here and your second pointer here. At each step of the iteration, you advance your first pointer 1, and you advance your second pointer 2. Then you advance your first pointer 1 and your second pointer 2. Your first pointer 1, and then your second pointer 2, right? So it gets the middle of the list by the time the last one gets to the end of the list, right? It's just that with reversing, it's possible to do it when it's just time consuming to do it when you don't have a second pointer. But I'm sure there's a more optimal way to do it. Let's see another one.
Talking about if you did that, then you could reverse that second half.
Let me just go ahead. I'm just trying to think of another one that would be good. Because I'm trying to avoid all the questions that I'm going to be using, right? So let's go. So let's go ahead and so let's talk about. Let's see. let's see, what should I do? Removing duplicates. So, let's see, we did merge a while back. It's just that I've done a lot of the good problems that I like. Oh, I think this was the one I was looking for. Iterate down a list using a pointer to change a reference pointer, build with tail pointer, build temporary dummy, build count. Write a count function that counts the number of times a given int occurs in the list. That sounds kind of terrible, but let's see. Nth, that gets it takes a linked list and an integer index and returns the, right, so that's the get one. Delete list, pop, let's see, insert nth there, insert in a sorted list, append, right. Remove duplicates. Let's see. Ooh, that one looks promising. Write a function called alternating split that takes up one list and divides its nodes to make two smaller lists. The list sublist should be made in alternating elements. So, if the original list is A, B, A, B, A, then one sublist should be A and the other should be B. You may want to use move node as a helper. I mean, I don't really need to do that. I can just do that as a static method, but it's still straightforward. So public static E. I'm not going to use any. I'm just not going to return anything here, right? Because I'll leave that as an exercise for you guys for what you want to return. But what was it? Split, alternating split. Yep. Split. Alternating split. And it takes in a linked list. Let's make sure I understood it right. Okay, yeah, so source. Yeah. Okay, so we don't return anything. Instead, we have our source list. That's what it has. We have our source list. A and B. So this may seem a bit weird, but what we're doing is that the way they defined is that we're passing in two linked lists. The ones we're passing in two linked lists here. The ones that basically that we're going to add our items to. So this depends on how we solve it. Depends on whether or not there's a tail or not, and whether you're inside of it. But I'm going to assume that we're just using a linked list class. So first off, we need to go and iterate through source. So for e item in source, we need to be able to tell whether we're going to add it to A or add it to B. But we don't know what index we're at because it's a bit difficult to keep track of our index. So we can just simply say, so let's just create a Boolean. Boolean add to A is equal to true. Okay, so what we'll do is that if add to A is true, or we can just simply say if add to A, then we want to add this item to A. So A dot source dot. Oh, but you can't remove the item from our source. Yeah, but we can't. But again, we're in a static method, so we can't reference head or tail or anything. So it A dot add item. I'll go. Yeah, it's much more interesting if it's an instance method, which I'll show how to do in just a second. Else. Yeah, I know that we're done. So if you need to leave, you can leave. B dot add B dot item. Let's see. So if else, and then finally, so if we're on A, we want to add to A. Otherwise, we add to B, and then otherwise, we say add to A is equal to not add to A to flip it, which is the entire reason I bothered doing it, because that's a nice little trick there. Okay. Now suppose that this is a now suppose that this is instead of this being a linked list like this and is a static method. Now suppose instead that it's a instance method, public void alternating split, node e source, node e, node e. Where each of these are the heads of linked lists.
So what about the, next method? What is it?
The next method,
Next?
we don't need to use. Well, I'm inside the linked list method now. I'm rewriting it inside. So same over here, and instead over here we'll do a while loop. While source is not equal to null, what we'll do is that we'll say we'll add over here an iteration through it. Source is equal to source.next, and this won't hurt. And this won't make us lose our original head because we're not going to lose our original head because that's stored in a memory location outside of this method, right? So now if add to A, what we do over here is that we do A dot next is equal to new node source dot item, and then we say A is equal to A dot next to advance A. Yes,
Wouldn't that return the pointer though to the very end?
that will move it to the very end. Yeah, because so when we're adding it, so what we're going to do is that we want to add it to the tail of the list. So right now this is an empty list, or rather, actually that would be an empty list. So that actually does make it slightly problematic. So we'll have to add another condition there, assuming those are empty lists. But
Right, so is it, so can we use like,
but let's.
A dot add and A dot next?
They're nodes. They're nodes, right?
Does A dot add the object?
Let's
of
see.
the void method for?
Let's see how. Struct node, B reference, A reference. Yes.
Would you post setup for this problem, because I don't think we have it in linked final.
I'll upload this video. Yeah.
I'm just looking at these, like I'm trying to see. Is this?
That's for an
Oh,
iterator.
that's only for the iterator.
That's for an iterator.
Shoot, okay,
That's for if you're using an iterator.
okay.
So A.next else B.next is equal to
So
B.
we can't, the only add we have is add last. Adds an object to the end of the list, add first
So-
or add last, okay.
A.next is equal to
With get first, get last, and add first, add
here we
last.
go. A is equal to this new source dot item. So, and then, so here we go. If A is equal to null, A is equal to this is equal to source dot item, else A dot next is equal to new source dot item, and then A is equal to A dot next.
So
Regard.
their linked list class is the double linked list, is the thing, right?
Yes, I
Okay.
believe so. I think this would solve it. So that looks like it would solve it. So A B is equal to, yep, so if we start a node, and then otherwise we set the next node to be ours, and then move forward to the next one. And then we'll have the original reference to the, actually, no, that wouldn't necessarily work, because we'd have the original, node A, so node orig A is equal to, so node orig A, node, so node, head A, head B, here we go. Again, it's the question of,
You're only gonna enter that part once for the first time you add it, really?
in some, yeah, sorry, so let's see, some of the elements in the list may be in any order. It's just the whole thing about, like, you're passing in this empty, it's just the way that they have done it, which is that if we were passing in a list, that would be one thing, right? Because we'd have the head.
And why
But if
is
they're
it
passing in a
passing-
node, that
Oh,
makes,
they're passing it in as three things.
as a node, right?
Oh, let me see, okay.
Oh, but they always do it as a node. That makes sense. So if we were passing it in as some other linked list, then
Right.
it makes it easier. But I don't think with the way,
So how are they passing, can I just see it? Can you-
well, they're doing it in C++.
Oh, I see.
That's what makes it a bit different. See,
And they're passing in node structs, yeah.
oh, but it doesn't matter if they
But they're
don't.
two-pointers.
But it doesn't matter if they don't need the nodes back. If they just want to
Right,
split
right.
it, if they don't need the original things back, then this thing will just, then this will work just fine. And then basically what we can do is that at the end of this, to have our original nodes, we can say head A is equal to, A is equal to head A,
Right,
B is equal to head B, if we want to get our original points back,
right,
right? Which
Okay.
I assume we do.
okay. Okay, got it.
It's a bit of a weird question, but it's also weird by the fact that
Yeah, so if this is like, so if we were saying, so what they're like, we're saying it's like two empty lists, basically.